right, we're back. Chapter 13.3 is what we're on today. So the reading starts on page 318 and it goes to page 324. Okay, we have talked about electrostatics, what it is, about how it stores up electricity on an object. We've talked about how it transfers from one object to the next. You can use conduction, which is direct contact, which permanently changes the charge from the one object to the other, or allows them both to now have a charge. Or it can be induction, which is when there's space from the charge is imparted from a distance. Okay, and so that's where it like jumps, like you see in lightning. So today we're going to talk about how we apply all of this to science and why we even need to learn it. Okay. We're going to start by talking about what an electrostatic generator is. Okay. It is essentially a device that's used to produce static electricity. Otto von Guericke is the one who is credited with discovering this. And it's essentially just, like it says, a device that can create this electrostatic charge. Now, why would we need that? Well, if you look at page 319, there is a picture of the Van de Graaff generator. Okay, Van de Graaff generator it's kind of like, you've seen pictures of this, you'll see it in your PowerPoint, but essentially it's one of those devices that where you touch it and then like all your hair goes all over the place. Okay, because it's imparting that electric static charge to all of your hair. And there's a picture of that in the PowerPoint. But essentially what it does, if you look at the picture in your textbook here, okay, there's a belt that conducts the electrons up into the sphere, and then the charge actually spreads out throughout the dome, okay, throughout the outside of this dome. That's where the charge goes, okay. Now, this is a really important concept because it allowed us to understand that ways to keep ourselves safe. So you might have heard of a Faraday cage before. If you've ever watched Lost in Space, Sam and I just watched that together, and the pods that it's like a spaceship that they're in, the spaceships are actually Faraday cages. And essentially what that means is they go to these areas that have lots of lightning, and if they're inside their Jupiter, which is the spaceship, then they're safe because electricity wants to go to the outside of an object. So think about it, if you are in a lightning storm, but you're stuck in your car, okay? And you think, oh goodness, this is not good because I'm stuck in this big metal contraption. Actually, it is good, because if lightning were to strike, it would go to the outside of your car and it wouldn't go to the inside. It's kind of acts like a mini Faraday cage. And so that's what we discovered when we found this lightning machine that Van de Graaff created. And so these charges would go to the outside. Now, depending on the shape that you're in, the charge can be concentrated in different areas. So if you look on page 320, there's a picture here of the two different shapes, okay? When you have a point, the electrons can concentrate at that point. So that point is going to have more of an electric charge than if the shape is a dome, okay? And where all the sides are equal. So it's more concentrated at a contour of a sharp curve, okay? Now, from all this, we also can jump to talking about lightning. And in your PowerPoints, I included a couple videos that talk about how lightning works, and then a person who was able to catch some pictures of lightning. It's kind of interesting to see how it all works, because when we think of lightning, we just think of it coming straight down to the ground. Well, how does that even work? Well, let's talk real quick about Benjamin Franklin and his famous experiment, and then we'll talk about how the anatomy of what a lightning bolt is like. Okay? So in 1752, Franklin created this experiment, and he essentially took a silk kite and he put a real sharp metal like piece on the end of it. Then he had tied string to it, and then he had tied to the string, he had tied some silk that he held onto. And he set the kite up in the middle of a thunderstorm. Now, this is extremely, extremely dangerous. And he knew it was dangerous, but he didn't realize just how dangerous it was. Had lightning struck his kite, he would have died. but essentially he thought because he was dry and safe under his shed, and that he was holding the silk and not the string, he thought he'd be fine. But essentially what ended up happening was the kite went up into this thunderbolt, and when he brought a little, on his knuckle he had a little piece of metal, when he brought that close to the string, a little tiny lightning bolt went from the string to the little metal thing on his knuckle, okay? And so he realized in that moment that thunderclouds have a lot of electricity in them, static electricity, because they're not going anywhere. But then when they give lightning, once the lightning bolt actually takes place, then that's that current electricity, where the electricity travels. So static electricity is up in the cloud, where it's all just collecting until we have the lightning bolt actually come to the ground, and that is your current electricity. So current electricity there's a couple parts of the lightning that I want you to know about, okay? The stepped leader, and this is in your notes, your stepped leader is the initial stream of electrons that moves from the clouds to the ground. So it's that lightning bolt that starts to zigzag its way down, okay? And in the video, there's a lot other different parts to the lightning bolt that they'll go through that are interesting to know. But the two that you really need to know are the stepped leader, which is the lightning bolt that starts to come down, and then the positive streamer. Now, the positive streamer actually comes up from the ground, and that's what's cool about the one video. It shows the picture of it coming up from the ground. So there's a lightning bolt coming down and a lightning bolt actually that comes up from the ground, and then they meet. And so the lightning bolt from the ground is called the positive streamer, and the lightning bolt that comes down from the cloud is called the stepped leader, okay? And they take an interesting path on their way to it. So check that out in the video that I sent you in your PowerPoint. The PowerPoint's available on RenWeb. So just go to RenWeb under lesson plans. It's going to be under documents for you, okay? And you'll just click onto it and it should pop up. If the videos don't work, let me know and I will, I'll send you the links, okay? So how do we protect ourselves from lightning? You know, we talked about a Faraday cage and how that can divert to the outside of a metal case, but there's also lightning rods. These are like antennas that are on the top of buildings. We talked about this the other day. And if lightning were to strike, then that it would strike the lightning rod, because lightning is always attracted to the thing that's highest. So it goes to the lightning rod, and then the lightning rod is actually going to be connected via metal all the way to the ground. And so the electrons will travel through the lightning rod to the ground where it can get grounded. And if you remember from grounding, that's just the earth is so big that it absorbs that electrical charge. And so it kind of diverts it from any place that you would not want it to be. Two or three more devices I want to talk about. You can read about St. Elmo's fire on page 322. It's just like this bluish glow that comes in the middle of like when storms are accumulating, and it gives kind of this glow. So you can read more about that. But then there's the Leyden jar. Now, Leyden jars are named after the University of Leiden, which is in Holland. And a fun fact, my sister actually lived there for a little bit. But a Leyden jar is essentially a jar that can store static electricity. And so Peter von Mussenbroek, okay, he created this device. And on page 323, it talks about how it works, okay? So if you look at the different pictures, you have, it's got a cord over here where the electrons are being repelled to the ground. Oh, you can't see. There you go. It's got a metal pole over here with lots of electrons on it from an electrostatic generator. Remember, that creates the electric charge. And then you hit it to this brass rod, and then what happens is the electrons can kind of congregate in here. Then when you take it away, it just stays there. All those electrons are still in there, and then you can actually take them out and extract the charge when you need it, okay? So that's a Leyden jar. And then there are three things. Oh, no, one more. A Leyden jar is essentially an early type of capacitor. Excuse me. If you've ever, like, taken a picture with a nice camera, you hear that sort of whir that's there. That's the capacitor. Essentially what the capacitor is doing is it's like releasing that electricity all at once. So it stores it up and then it releases it. And so that's really helpful, obviously, in flash photography when you need a flash and that electricity, that electrical charge, you need it all at once, a little burst of electricity. And so that's where we get that from the capacitor. And there's some pictures of capacitors in your textbook. 3 other devices. The photocopier uses electrostatics. I included a video that talks all about how that works. But essentially it has to do with positive and negative charges and how you can like use that to create an image. And so it's kind of an interesting, if you didn't know how photocopiers work, it's kind of an interesting way to figure that out. Air filters and car paint, okay? Read about those in your textbook. It's going to talk about how they use this charge to keep the paint all in place or to filter the air. So anyways, that is for you to do your reading on. Your homework is 13.3, 1 through 6. And just take a picture and send it to me. And then the rest of this week, we're going to do some review. And I've got a little quiz for you on Friday. So anyways, feel free to text or call if you have questions. If you haven't gotten me your tests yet, please do that. And make sure you're staying up on your homework. I don't want you to have to do anything over spring break. If you haven't worked on your science fair project, work on your science fair project, okay? This is a perfect time to get a lot of that work done. It's a lot of work, and you don't want to come back from spring break with so much work to do, okay? All right, love you guys, and we'll talk soon.